Hi, so I think this is the 5th video in our fundamental particles series, and it's the second one specifically about muons and pions. So before we start, let's just summarise where we were, or where we are, as far as the course is concerned, in terms of the fundamental particles we know of and what groupings they fall into. So we have two groupings. We have the fermions. And so far, the fermions consist of our two nucleons, and although we haven't really dealt with them, probably they're two antiparticles. And the electrons, of which we have the electron, the positron, and the real and anti-electron neutrinos. So there are fermions, and then the other exchange particles, groupings that we have are the exchange bosons, the things that as virtual particles mediate the various interactions or forces that are responsible for the behaviour of nature. And the first one that we met that was sort of proposed by Einstein is the photon, and it is the exchange particle for the electromagnetic force. We've now looked at the two W's in some detail, the W plus and the W minus. We haven't said anything really about the Z naught, but then we don't. It's not really on our course. Z naught is how neutrinos bounce off each other. And they are the exchange particles for the weak interaction, and the weak interaction is the interaction responsible for most particle decay. I've also popped down here, but greyed out, the couple of others that we've heard of, which are the strong force, and the strong force's exchange particles are gluons. That's we haven't really got into what any of that means just yet, and we won't really go into it in any detail at any point. It's not really our course. And then there's the graviton, and I've mentioned the graviton before and mentioned the fact that it hasn't been discovered. It's too weak for anybody to even know how to set about discovering it, and that quantum mechanical gravity isn't the same thing as general relativity gravity, and so it's one of physics' conundrums whether that one even exists. But anyway, there we are, two fundamental groupings, which between them pretty much explain all normal matter. In fact, the only thing that was missing was something to stick the nucleus together. We needed a set of exchange bosons to stick the nucleus together. But instead we found the muons. So we found the mu minus and the mu plus, these highly penetrating particles that will be informed by cosmic rays, making it down to the surface. But at the same time, or immediately after the war instead of immediately before the war, we also found the pions. And the pions are Yukawa's particles. The pions are the exchange particles that stick the nucleus together. And so in our sort of semi-classical thinking about how the universe works, they complete this list. And so we don't need anything extra. So we can redraw that. So that now I've taken out those greyed out ones that aren't really part of our course, and I've popped in the pions as being the exchange bosons for the strong nuclear force. So there you go. That's all we need. They provide that set of particles provides enough to build all normal matter. The things that you and I are made out of, the things that stars are made out of, basically everything is made out of those things that are presently on that page. We don't need anything else. So that, of course, raises the question, what the hell are these things? Why have we got them? Who ordered that? I've put that there because that was very famously said about the muons by this chap, Isidore Rabi. And those of you who do chemistry will learn about Rabi because you have to do NMR. It's part of the chemistry course. And of course, everybody else owes something to Rabi because NMR is very closely related to MRI, which may one day be partly responsible for saving your life or putting something right. So it's pretty important. So Rabi was a particle physicist. He, I thought I'd shut my cat out. My cat's just arrived, so I'm laughing. Sorry. He was working on particle physics and looked at the muon, and like everybody else, just thought, we don't need that. Everything else on this page, we need those muons. They've just complicated things utterly unnecessarily. We were thinking that physics was done. We were going to be able to put our feet up and smoke a pipe. And my God, we got these muons. What the hell are we going to do about these? How do we explain these in our grand scheme of things? Well, that's something that we'll get onto a bit further. But for now, let's have a look at the behaviour of pions. So their rest energies are intermediate, about 300 times that of the mass of the electron, and they've got quite short lifetimes. So the charged ones are on the order of 10 to the minus 8 seconds, and the uncharged one 10 to the minus 17 seconds. So the uncharged one, the Pion, really does not spend any time at all before it disappears, and that it's a detail that you don't need, but it's on the course. That's not on the course, is because the two decays are mediated by different forces. So this 10 to the minus 8, that's mediated by the weak force, whereas actually it's the electromagnetic force which is stronger, which is why the weak's called the weak, which mediates the disappearance of the pi zero. So it happens in a faster timescale because it's a stronger force. Anyway, and just what else was saying, pi naught, the other things about pi naught, of course, is that where it has no charge, it wasn't discovered in cloud chambers in the same way that the other two were. So the pi naught is not found until later. Convincing evidence for its existence is not found until later because where it hasn't got a charge, it's not leaving those ionized tracks in cloud chambers or in photographic emulsions. So the things that we were looking at for the discovery of the charged pions and the things we were looking at for the discovery of the muons do not hold for the pi zero, but or the pi naught, but it's definitely there and was found in the 50s. So key facts about pions created in very, very energetic nuclear collisions. So this is we were talking about last time. Protons being accelerated by processes around black holes. So the protons are going at unimaginable speeds, smacking into the top of the atmosphere and creating pions. These days we do it with the same kind of thing with the Large Hadron Collider. Now the charged pions are their own antiparticles, are antiparticles of each other. So the pi minus is the antiparticle of the pi plus. So an anti-pi minus is a pi plus, and an anti-pi plus is a pi minus. That's unnecessarily complicated to write it that way, so we just stick to using their charge the same way we do with the positron and the electron to be able to distinguish those apart. The interesting bit, however, is that this one is its own antiparticle. And that's interesting because it's quite a regular exam question. They quite often say which particle is its own antiparticle, or they'll say, or they'll be part of a multiple choice or something like that. So that's just one of those things that you have to know. So write that down somewhere. It's necessary knowledge. The why the pi naught is its own antiparticle will become obvious later on in the course. They're the exchange particles for the strong nuclear interaction. That's also required knowledge for the course. You don't really need to know anything more than that. You just have to be able to reproduce that phrase there. The charged pions decay into muons. We know that already because we had a look at some of the Bristol group's emulsions in the last one. And the uncharged one decays into gamma photons, usually. Now, they are the exchange particles for the strong nuclear interaction. And so I've put this graph in here. It's a bit of a schematic graph rather than a real one, but it sort of gives you the idea of what's going on. And most importantly, you have to be able to reproduce this graph. So you have to be able to sketch this. knowing that this is the attracting side and this is the repelling side, you have to be able to sketch this graph. And what's it demonstrating to us? Well, it's demonstrating to us the forces within a nucleus. And so we have the strong nuclear force attracting the protons and the neutrons together, and we have the electrostatic force that's trying to push the protons apart. And the combination of these two is what holds a nucleus in place. And as I say, you have to be able to do a sketch of this, and having sketched it, you have to put some figures on the x-axis. So this crossing point here is somewhere in the region of 0.5 femtometers. And this strong force starting to tail away is somewhere in the region of 3 femtometers. And so you have to be able to sketch this graph and put those values on. Now, these values are changeable, shall we say. They vary depending on exactly on what the composition of the nucleus is. I was reading when I was trying to sort of verify this for you and try and find some less schematic graphs for you, that actually the combination of the red and the blue lines doesn't become positive until we get out to 12 femtometers. When we get out to 12 femtometers, then the combination of these two become positive, whereas it looks here like the combination of these two is already positive, after about 1 femtometer. And so when you get out to 12 femtometers, that's why big nuclei are not stable. 12 femtometers, 12, 14 femtometers is where we get to uranium. Anyway, that's not what's required for the course. What's required for the course is these. So there you go, I've just written that out again. And a note that this is required. So pause the video, get this sketched, get those numbers written down. You have to be able to draw this in an exam. It's specifically in the syllabus. Okay, now a pion is a charge, can be a charged particle. So a pi minus is going to be attracted to the nucleus. We mentioned that very briefly in the previous lecture. So not only is a pi minus actually attracted to a nucleus, but if a pi minus is moving fairly slowly and comes close to a nucleus, it'll actually join the atom. It will, and it'll have energy levels just in the same way that an electron will have energy levels. Just that its energy levels will be hugely lower. I say lower because they're negative. Because the mass term appears in the calculation for the energy levels. And because the mass of this is much, much higher than the mass of an electron, its energy levels are much, much, much lower. And so when a pion joins an atom, it kicks out some of the electrons, some of the energy that the pion gets by joining, the drop in energy that the pion gets by joining the atom. It manages to get rid of that energy by transferring it to some of the orbital electrons. From then onwards, as it drops lower and lower down the energy levels, going down to the lowest pion energy level, it emits X-rays, and we can detect those X-rays. Now with a pion, it won't get down to the bottommost energy level. It won't get down to 1s, or it won't normally get down to 1s. It might get down to 1s on a very lightweight atom, but on something heavy, long before it gets to 1s, it will have seen the nucleus. I say seen, the wave function of it and its W's will start to overlap the wave function of the nucleus, and the nucleus is W's. And so there will be an interaction between the two of them, and the pi will interact with the nucleus, and the pi does this. Now you can see why that works, because this has got a positive charge, that's got a negative charge, and that's got no charge. And so as far as charge is concerned, that's fine. As far as nucleon number is concerned, that's a real nucleon, that's not a nucleon, that's a real nucleon, that's fine. So you can see that that works. What I think is also clear, or I hope it's clear if you've been paying attention, is that there aren't any other rules. When an electron did this, when we had electron capture, we had to create a neutrino to compensate for the loss of the electron. We don't have to do that with the pion. The pion doesn't have any extra conservation rules associated with it. So pion capture, a negative pion, first of all joining the atom and becoming a pionic atom. It really is a real thing, but it's a real thing that exists for 10 to the minus 8 seconds or less. Hard to imagine that physicists do experiments on these things and discuss their existence, but they really do, even though they might only exist for 10 to the minus 10 seconds. Physicists worry about them. They do measurements on them. They do calculations on them. It's extraordinary. And as part of this process, of course, this disappears. And this has not an energy of half an MeV in the way that an electron does. This has got an energy of 136 MeV. This is a lot of energy suddenly being deposited upon the nucleus. And it depends on the nucleus and on the circumstances as to exactly how that energy gets dealt with. But one of the things that can happen is it will blow the nucleus apart. That sudden arrival of 136 MeV or 137 MeV on the nucleus can blow the nucleus apart. And that is what this over here is a photograph of. This again is from Powell's group in Bristol. This is one of the very earliest pictures of the death of a pion. So what we've got is a pi minus here, giving us a nice thick heavy track, so we can know that it must be going quite slowly. And it meets an oxygen atom. Within the calculations say that within 10 to the minus 13 seconds, our pion has dropped down to the lowest possible energy level and seen the nucleus and absorbed onto the nucleus doing this. And in this case, it blew the nucleus apart, blew apart the oxygen. And one of the things that makes this an interesting diagram, you can see it labelled there, is that this little, it's called a hammerhead formation there, and that is part of the fragments of our oxygen blown away was beryllium-8. So that's 4 protons, 4 neutrons. And our beryllium-8 is carrying so much energy away from this explosion of the oxygen that our beryllium-8 then blows up itself and fires out a pair of alpha particles. And so what we've got here is the 2 alpha particles, the tracks of the 2 alpha particles being fired out from the beryllium-8 splitting apart as a consequence of the oxygen having split apart. How fantastic is that? And when we were looking at these before, I said they're, sort of 2 millimeters. Actually, I was wrong. Scale on this is something like that's more like 10 microns. So yeah, tiny scale we're looking at here. And we Powell and his group, Occhialani, managed to capture this brilliant image of the pion destroying the oxygen. Okay, let's have a look at the decay of pions. So if pions don't meet an atom, or they're positives, or they get repelled away from the atom, then how do they decay? Well, we've already said that the pi zero decays into gammas, decays into 2 because if it only decayed into 1, it would be almost impossible to conserve energy momentum. So it has to decay into 2 so that they can share the energy between them and by going off in different directions, deal with the momentum that the pi zero had before it decayed. There's other things it can do. So it could make 1 gamma and then do pair production. So you can see that there's no problems here. There's no charge there. And then we make a positive and a negative charge. There's no electrons there, but we make a real electron and a anti-electron. And so all of our conservation rules are are perfectly conserved by that, and there's no particular conservation rule for the pions, and no extra conservation rule for the pions that prevents that from happening. So this is the most common one, but that can happen. Now, for the charged ones, the most likely decay is into a muon. And there you go, there's the decay into a muon. Now, when we talked about this in the last video, I said that a neutrino was being formed at the same time, and you can see here that we've formed a real muon and we've formed an anti-muon neutrino. Now that should be familiar to you. That should seem familiar. If we have a look at it for the electron, this happens much more rarely. This is the common one, but it can do the second one. Then this should be very familiar to you. We have a pion decaying into an electron and a antineutrino. And if we think about the rules here, if we do charge, we've got -1 goes to -1 plus 0. And if we think about nucleon number, there aren't any nucleons. So if we think about electron number, then that's not an electron. That's a real electron. And that's an anti-electron neutrino. And so our rules are obeyed. So that is what's going on there. And by analogy, we can see that the same kind of thing is going on with the muons. And it doesn't take a genius to work out that if it was the positive one decaying, then it would be decaying into the positive muon, and it wouldn't be making a real muon decaying a neutrino. Or if it's decaying into a positron, then it's making a real electron neutrino. Right, muons also join the atom. Only the negative ones, obviously. Positive ones will be repelled away by the heavy nucleus. But a negative muon can also get captured by an atom. And it will do the same process as the pion does. And so as it first gets captured, the energy that it's lost, the potential energy that it's got rid of by joining the atom, is transferred to some of the external electrons of the atom, and they're kicked out at high speed. As it drops further and further down to lower and lower energy levels, it spits out X-rays, and you can see the picture over here. We can see the X-ray transitions. We've already done that for some of the transitions for normal visible light and ultraviolet light when we were talking about electrons joining hydrogen. Well, this is muons joining oxygen, and they're X-rays that are being kicked out as the muons do the transition. And then superimposed upon that, you can also see that these guys were also measuring pions. So that's a pion one that's superimposed on top of the muon ones. So we get what's called a muon cascade. We get all of this energy being pumped out as it drops from energy level to energy level to energy level, and the energy levels are much more energetic because of the much larger mass of the muon. And so there we get a muonic atom forming. And of course, these ones, in physics, particle physics terms, last quite a long time because a muon is on the order of 10 to the -6 now, instead of the much faster decay away of the pion. Plus, the muon doesn't show anything like the same interest for the nucleus. It's not your Carver's particle. It's not there to get involved with the nucleus. So the muons, once they join an atom, always do get down to 1s. They always do get down to the muonic 1s. So there you go. We cascade down to the muonic 1s, releasing X-rays as they go. Now, as I was thinking about this, I was thinking that the muonic 1s must be related to the electronic 1s, and that the electrons would have to be kicked out of the way. And actually, of course, I realised I was wrong, because Pauli's exclusion principle doesn't apply here, because the muon is a completely different thing to an electron. So that we can get muon sitting in the muonic 1s, and we can get electrons sitting in the electronic 1s, and the two of them don't talk to each other. The electrons get kicked out because it's just a way for the muon to get rid of all of that energy as it's dropping down, which I thought was interesting. And chemists do chemistry on muonic atoms. I know, amazing. Who knew chemists did anything? Yeah, at a 10 to the minus 6 existence. Amazing. Right, once it's down in 1s, it's got two choices. It can either decay, as if it were a free muon, or it can do muon capture. And which one it does depends on the nucleon number of the atom that it's joined. And this is the reason why that experiment by the Italians at the very end of the Second World War, where they found that negative muons did indeed all do capture on the nucleus when they used an iron moderator, an iron lump of iron to slow down the incoming muons, but that the muons didn't all capture onto the nucleus when they used a lump of carbon. They got this different behaviour between the two of them that, if you remember, at the end of the Second World War, nobody could explain, and was why everybody came to the conclusion that muons probably weren't your Cartwright particles. And that's because the likelihood of the muon doing muon capture on the nucleus depends upon nucleon number. Higher the nucleon number, the more likely it is for the negative muons capture onto the nucleus. And so for lightweight nuclei, the muon is probably more likely to just decay away and therefore fire out a decay product that the Italian experiment could then detect. So what is muon capture? Well, that's muon capture. And again, if you've been paying attention as we've been going along here, that should be entirely familiar. You should have seen an equation that looks incredibly like that before. So you should understand what's going on there. If you don't look at that, and you don't think to yourself, do you know what, I know what's going on there, then you haven't understood beta decay, and you've got to go back and have another look at the types of beta decay video. So if that doesn't ring huge bells with you, go back and have another look at the types of beta decay video, please, because it should be obvious to you what's happening there. But as with the Pion, we deposit a lot of energy, not quite as much energy as the Pion, but nearly as much energy as the Pion, into the nucleus from the disappearance of our muon. So this is an example I found on a paper online. So this is silicon doing muon capture and forming aluminium. But that little star there tells us that the aluminium is excited. So the aluminium's got to find some way to get rid of all that extra energy that it's gained in this process. I suppose it could do it by firing out a gamma ray. Some of it can go out with the muon neutrino that is formed. But some 50% of the time, it does this. It actually fires out a neutron as well. It uses the energy of this muon that's been deposited, not only to change one of the protons into a neutron, but actually to fire one of the neutrons out. And of course, that better balances up the aluminium and makes it closer to stability. And the neutron can come out with quite a bit of energy. Some of the time, I forget the exact number, something around 20% of the time, it'll actually kick out two of them. It'll boot two of the neutrons out and bring the aluminium much closer back to stability. And 1% of the time, it'll actually boot out three of the neutrons. So the muon does muon capture, deposits a lot of energy on the nucleus, and the nucleus has to deal with that. When we're looking at that Pion example earlier on, the nucleus dealt with it by just disintegrating. This silicon, the nucleus deals with it by kicking out some of its neutrons, and those neutrons take kinetic energy away, and it also allows the nucleus to rearrange itself to a more stable form. Right, I've given you enough clues. If you haven't worked it out by now, then you really haven't been paying attention. Muons are fat electrons. All of those behaviours If I get rid of a muon, I've got to create a muon neutrino. If I make a muon, I've got to make an anti-muon neutrino. All of those behaviours should have been telling you that muons are fat electrons. That those behaviours were all identical to the behaviours that we saw in beta decay. As I said on the previous slide, if you haven't got that, go back and look at beta decay again, because it's important that you see the connection. So rest energy is that. It's a bit less than that of the Pion. What was the Pion? 137, and this one's 105. Almost exactly 200 times, 207 times the mass of the electron. So you can see why people were excited by the muon when they first discovered it, because this really is bang in the middle of where our analysis based on sort of Yukawa's ideas said that we ought to be finding a particle. Wrong particle. It was a Pion, a bit heavier, but there you go. And it's an odd one, this. I've seen a couple of exam questions, not for a while, I have to admit, but I have seen a couple of exam questions where it's a whole lot easier to answer the exam question if you know that the muon is 207 times the mass of the electron. You know, if you've got to talk about why they decay and things, if you can mention that 207, you get yourself an extra mark off the mark scheme. So it's a useful one to have written down. You don't have to have these numbers memorised, but knowing that 207 is a good idea. Mean lifetime, there you go. You can see it hangs around longer than the Pion, but still decays away using the weak interaction. And so this is a sort of characteristic timescale of a weak interaction decay. And because they're electrons, they must also come with their own neutrinos. And so we have real muon neutrinos and we have anti-muon neutrinos. And yes, we do know that they are different from electron neutrinos. Hard to do those experiments, but for example, a muon neutrino will not do electron capture on chlorine and release an electron. Sorry, not an electron capture, a neutrino capture on chlorine. We talked about the Homestake experiment. A muon neutrino won't do that. Electron neutrino will do that. Muon neutrino won't do that. A muon neutrino with enough energy could do muon neutrino capture and make a neutrino, but it can't make an electron. They are separate things. So muons, fat electrons that come with their own set of neutrinos, which are different from electron neutrinos. And so because we've now got not just electrons, we've now got electrons and muons, we have to give this a new family name, and that family name, well, I've mentioned it once or twice in hints up till now, is leptons. So electrons and muons are in a family that we now call leptons. Right, let's have a look at muon decay. So muon decays to an electron and an anti-electron neutrino. Or does it? Actually, it does that. Why is it doing that? Why do we need the extra neutrino? Well, let's have a look at the numbers. So first of all, we've got to do charge -1 goes to -1 plus 0 plus 0. Charge is good. Let's do lepton number. Well, our neutrino there, our muon there is not an electron. It's a different flavour of lepton. I know flavour seems silly in this context, but it is the right word. Our electron, that's a real electron. Anti-electron neutrino, that's an anti-electron. Our muon neutrino, that's not an electron lepton, it's a different flavour of lepton. So yeah, that works. So why do we need this other muon? Well, we need this other muon, this muon neutrino, because there's also a, sorry, struggling with the pen, there's also a muon flavour lepton number. So our mu minus arbitrarily is the real one, like the negative electron is arbitrarily the real one. So that is a real, I don't know why I wrote minus there. That's a real muon. Electron, different flavour, not a muon. Electron neutrino, different flavour, not a muon. Real muon neutrino, that's a muon. And so muon lepton number is also conserved. So we've got this extra rule. We've now got both flavours of lepton must be conserved. So we have conservation of electron lepton number and we have conservation of muon lepton number. And that's called lepton flavour conservation. But collectively it's just called conservation of lepton number. So when you're answering an exam question and they ask for a conservation rule, you say conservation of lepton number. But if they ask you to do to work out what's going on, and you've got both muons and electrons rather, you've got to conserve both flavours. So slightly difficult. We're doing conservation of a lepton number, but within conservation of lepton number, lepton flavour is also conserved. But in your exam questions, that's the one you write down, but that's the one you do when you're actually working out what's going on. Good, eh? And what's more, just to add to the complication, there's one more. The tau. Sometimes called the tau particle or the tau lepton. It can also be called the tauon, but you almost never hear it. We're called the tauon. It's just called the tau. And it comes in positive and negative. And you're not going to be surprised right now because it's another flavour of lepton. It gets its own neutrino. It's huge. It's 3,500 times the mass of the electron. This is a biggie. And so this is not discovered until the 1980s. This is discovered in particle colliders where they were smacking electrons together at huge speeds in the 1980s. So this is not really on our course because our course stops in the 1970s. So all you have to know about the tau is that it exists. There is such a thing. And that's pretty much the extent of your knowledge. It's a clue that pairs of particles, come in 3 generations, getting successively heavier. So we've got the electron and the electron neutrino, generation number 1. Then we've got the muon, we've got the muon neutrino, generation number 2. We've got the tau and the tauon neutrino, generation number 3. 3 generations getting successively much heavier. And it turns out that rule of 3 follows through when we get later on in the course. But unfortunately, I say when we get later on in the course, it follows through when we get later on in particle physics. It doesn't follow through on your course because the last generations on your course weren't discovered until after 1970, and so on your course. So I've probably just made things complicated by wittering about that. Anyway, decay. So unusually, it can decay into pions. You can see here we've got rid of a real tau. We've created a real tau neutrino, so lepton number's fine. And we've talked about the fact there isn't really a conservation rule for our pions, so we can just knock up some pions. If that helps get rid of the energy from our tau decaying, then that's what we can do. So it actually does that most of the time. It can also do these two. It can create a muon, or it can create an electron, and create the usual neutrinos to match. Looking at it on the screen here, I don't seem to have the bars over the top of those. Maybe I just can't see them properly on the screen. So you can work out for yourself that doesn't add up to 100%. The tau can do a lot of other things as well. We've got just so much energy to spare. You know, it's massive amounts of energy, and so there's a whole pile of routes that are available to it, and that's what you use your Feynman diagrams for. These particle interaction diagrams that we've been discussing, you use those to work out all the possibilities for your tau. So if, for example, we were to look at that one, we would say that we've got a tau inbound. our tau is going to, staying with taus, going to become a tau neutrino. And it's going to get rid of all of its excess energy as a W. And that W will then decay into an electron and an anti-electron neutrino. And our negative charge is clearly flowing there. And so that must be a W minus. Okay, so we can work it out from just thinking about what's going on. This is the tau side of my diagram, this is the electron side of my diagram, and they're joined together by W minus. So even if they gave you something like this that isn't really on your course, haven't really come across before, you could work out what was going on. You've got the tools to think it through. Keep the same things together on the same sides where you possibly can. This one looks more complicated, but actually isn't. Again, we've got a tau. Staying with the taus becomes the tau neutrino, emits a W minus, and then the W minus decays to our pair of pions, pi minus, pi naught. Okay, so there's one more. So we have 3 generations, 3 flavours of lepton. And so we end up with a new classification. Our fermions have changed very slightly in that they're now, instead of having the electron as a class, the electron is now a flavour of lepton. And we've got 2 more flavours. This side hasn't changed. Won't actually change now for the rest of our course. That's it. We won't add anything extra to the exchange bosons, but we're going to add a lot more over here, and we might find a few more bosons, just not obviously exchange bosons. Right, in summary, pions are the exchange particles of the strong nuclear interaction. They aren't the exchange particles of the strong interaction, that's gluons, but they're the exchange particles of the strong nuclear interaction, which is a subtype of it. The pi naught is its own antiparticle. Turns up on exam questions, have to learn that. The strong nuclear interaction is repulsive below about 0.5 of a femtometer and drops away to nothing after about 3 femtometers. Again, just numbers you have to memorise. Muons are in the same family as electrons, but 207 times more massive. Another number to memorise. Along with the taus, they make up the lepton family. They're flavours of the lepton family. Each lepton flavour comes with its own set of neutrinos. Each lepton number in total is conserved. And when we've got different kinds of leptons being involved, lepton flavour is also conserved. That's why each one comes with its own neutrinos. And incidentally, before I leave this lesson, I might just add that also explains, or physicists think it explains, why it is that the Homestake experiment only found 1/3 of the neutrinos you're expecting, because the other 2/3 had become muon neutrinos and tau neutrinos in flight. And so why neutrinos do that is a massive conundrum in particle physics right at the moment, and massive particle detectors are being built to try and work out why it is things that leave the sun as electron neutrinos on the way between the sun and the earth change so that they become a mix of electron neutrinos, muon neutrinos and tau neutrinos. No one's really quite sure why they're doing that. No one's quite sure whether maybe there's a 4th neutrino. 4th neutrino could explain a lot of other problems. But we've already been into the fact that things come in 3s. So if that came in 4, that would be a whole new set of problems that would be opened up. So neutrino physics really is cutting edge. You might notice when you look through my sort of list of Scientific American papers that I've scanned for you and put in a folder for you to do a bit of extra reading with, that there's quite a few in there about neutrinos. They are the thing in physics at the moment.